Imagine trading in a spotty 3G flip phone for like a dedicated fiber optic broadband connection. You aren't just getting a minor upgrade there.
Right, you're stepping into a completely different reality of speed and capability.
Exactly. And well, right now, the electric vehicle market is undergoing that exact same massive technological leap.
It really is. I mean, it's a total watershed moment for the automotive industry.
Yeah, so if you are even remotely considering your next car purchase, we are going right to the center of it today to look at the 800-volt EV architecture.
Because the technology has finally matured, you know? The manufacturing scales have tipped.
Right. The mission for this deep dive is to figure out why this specific shift isn't just like some engineering flex.
hmm
It's actually the ultimate cost-effective choice for your wallet and your time.
Absolutely. And to map this all out, we've got a really stacked lineup of sources today.
Yeah, we're pulling from this deeply technical engineering paper from G-Tire, which takes us down to the microscopic level of high-voltage architecture.
Which is great because it kind of forces us to look at the raw physics instead of just marketing jargon.
And we are pairing that with a comprehensive market analysis of the 2025 and 2026 e-car generation, plus an infrastructure report from the Electric Charging Network.
Oh, and we can't forget that incredibly detailed European Commission Cordis report on electric motor power.
Right, right. So before we can talk about how an 800-volt system saves you money over the lifetime of a vehicle, we kind of have to establish what it actually is physically.
Yeah, let's unpack that because the immediate assumption when you hear 800-volt system compared to a standard 400-volt system is, well, we're just doubling the size of the battery.
Which is exactly what I thought.
Yeah.
Intuitively, doubling the battery means doubling the cost of the car.
It's like the most common misconception out there on the dealership floor. But the G-Type paper breaks down why it's fundamentally incorrect.
Wait, really? So we aren't just buying twice as much lithium?
Not at all. Let's look at a standard battery pack, say, with an energy capacity of 55.44 kilowatt hours.
Okay, keeping the math specific.
Right. Whether an automaker builds that pack for a traditional 400-volt car or a next-gen 800-volt car, it actually contains the identical number of individual battery cells.
Seriously, the exact same number?
Yep. 4,400 cells, to be specific. The underlying cell chemistry and the raw material costs remain completely flat.
Okay, so if we aren't expanding the physical footprint of the battery pack under the floorboards, where is the change happening?
The entire shift just happens in the wiring matrix.
Oh, I see.
Yeah, to build a traditional 400-volt pack, engineers might wire those 4,400 cells in what's called a 110 series, 40 parallel configuration.
Meaning they link 110 cells together in a chain.
Exactly. They link them in a chain to build the voltage up to roughly 400 volts, and then they lay 40 of those chains side by side to give you the necessary current capacity.
Okay, so to step up to 800 volts, they just reconfigure the Lego blocks, basically.
That's a perfect way to put it. They just change the matrix. They string twice as many cells together in a single chain, so 220 in series, which pushes the system up to 800 volts.
But because they're using that same pool of 4,400 cells.
Right. They now only have 20 of those chains sitting side by side. So the matrix goes from 110 series, 40 parallel, to 220 series, 20 parallel.
Wow. Okay, so the battery has the exact same dimensions, weight, and raw material cost. But the electrical delivery system is completely transformed.
Exactly. Which brings us to the actual engineering and cost benefits.
Right, because if the battery is the same, why does changing the wiring matrix make the car vastly superior?
It all comes down to a fundamental rule of electrical physics. It's the relationship between voltage, current, and power.
Let me guess, we're talking about the classic equation for resistive power loss.
You got it. Power equals current squared times resistance. Or, P equals I squared R.
Okay, as a quick refresher for everyone, because the current is squared in that formula, cutting the current in half doesn't just reduce the power loss by half. It actively quarters it.
And that quartering effect is the magic secret to the entire 800-volt architecture.
So by doubling the voltage to 800 volts, the vehicle can deliver the exact same amount of total power to the wheels while pulling only half the electrical current.
Precisely. A system that used to pull, say, 140 amps of current at 400 volts now only needs 70 amps at 800 volts to do the exact same amount of mechanical work.
That makes total sense. Think of it like a logistical shipping network.
Oh, I like analogies. Go for it.
So instead of sending 140 massive heavy transport trucks down a really wide highway at 30 miles an hour, which takes up a massive amount of space and causes tons of traffic friction,
Yeah.
you just send 70 sleek, aerodynamic sports cars down a narrower highway at 100 miles an hour. You're delivering the exact same amount of cargo to the destination, but with a fraction of the congestion.
That narrower highway is exactly where the cost-effective details emerge.
Okay, tell me more about that.
Well, the Cordis EU report pairs perfectly with the G-type paper here, because having the current directly translates to physical material savings.
Because the wires don't need to be as thick.
Exactly. Because the current is cut in half, the cross-sectional area of the copper wire needed throughout the car can be significantly reduced.
And nowhere is this more critical than inside the electric motor, right? Because electric motors are essentially just giant spools of copper wire spinning inside a magnetic field.
You nailed it. They require massive amounts of tightly wound copper in the stator. I mean, some 400-volt EVs use up to 4 times the amount of copper found in a standard combustion engine vehicle.
Wow, 4 times. That's a lot of heavy metal.
It is. But by moving to 800 volts and dropping the current, engineers can actually shrink the thickness of those copper windings by a factor of 4.
Oh, wow.
Yeah, the Cordis report notes that this reduction in copper shrinks the total volume of the electric motor by a staggering 30 to 40%.
Okay, so here's why your wallet will actually care about this. You aren't just saving the manufacturer money on raw copper.
Right, the benefits get passed along to the driving experience.
A 30 to 40% smaller motor means you are driving a substantially lighter car. And pushing a lighter vehicle down the highway requires less electricity per mile.
It's a compounding benefit.
Exactly. You are directly saving money on every single charge over the entire life of the vehicle, just because your car isn't lugging around hundreds of pounds of excessively thick copper wiring.
But, the physical weight reduction is really just the first layer of efficiency here.
Okay, what's the second layer?
It addresses the biggest silent killer of electric vehicle performance and really the primary enemy of long-term battery health.
Let me guess.
Heat.
Heat. Thermal resistance.
Yeah, I mean, we all know what happens when a smartphone is left in direct sunlight. The operating system gets super sluggish and the battery drains almost instantly.
It's brutal on the device.
I have to imagine a 1,000-pound lithium-ion car battery reacts the exact same way to excessive heat. The chemistry absolutely despises high temperatures. In a traditional 400-volt system, pushing a massive volume of current through those high-voltage cables, the fuses, the battery management system, it generates intense electrical friction.
And that friction just bleeds out as heat into the chassis.
Right, it results in resistive power loss.
So basically, you're paying for kilowatt hours at the charging station, and instead of that energy moving the car forward, it's just literally heating up the cables under the floorboards.
It is entirely wasted capital.
Yeah.
But here's what's fascinating. The G-Tire paper includes a really compelling statistic from their cable analysis.
Lay it on me.
If an automaker keeps the physical thickness of the conductor wire the same, but upgrades the architecture to 800 volts, halving that current, the power lost as heat drops by 75%.
Wait, 75%? That is a massive efficiency gain.
It's huge.
But the implications have to go way beyond just getting more miles out of the electricity you paid for, right?
Yeah.
Because heat does permanent physical damage to the battery over time.
Oh, definitely. It degrades the internal chemistry.
Like how fast are we talking?
Well, when a lithium-ion cell runs hot during heavy acceleration or fast charging, the solid electrolyte interface, the SEI layer inside the battery, starts to thicken.
And a thicker layer's bad, I assume.
Right, because as that layer thickens, the internal resistance of the battery goes up, which permanently reduces the amount of charge the cell can hold.
Ah, I see.
But because an 800-volt system generates a fraction of that thermal stress, the battery cells stay significantly cooler under load.
Meaning the degradation process is radically slowed down.
Radically.
For someone buying a car and planning to keep it for like 10 years, this changes the entire total cost of ownership math.
Oh, without a doubt.
I mean, a full battery replacement is easily the most expensive maintenance cost on an EV.
Yeah.
So delaying that by years or avoiding it entirely makes the initial investment in 800 volts incredibly cost-effective.
It protects the core asset of the vehicle,
Yeah, but I want to challenge this engineering narrative just a bit here.
Okay, go for it.
We've established that having the current means we need smaller copper wires, smaller motors, and we generate drastically less heat.
Right.
But does every single component under the hood shrink? Because, I mean, at 800 volts, the electrical pressure is literally doubled. Surely some parts of the system struggle to handle that kind of intense voltage.
And that is exactly the primary engineering trade-off. You hit the nail on the head.
Okay, so what actually gets bigger?
Well, While the motors and cables get smaller, the components that actively manage the power face vastly greater electrical stress.
Like the inverter.
Yes, specifically the inverter, which changes DC power from the battery into AC power for the motor and the onboard charger.
Right, because high voltage wants to jump gaps. It wants to arc.
Exactly. 800 volts will stress materials and jump clearances far more aggressively than 400 volts ever would.
So how do they stop it from just short-circuiting everything?
To prevent catastrophic failure, the internal circuits of the inverter require wider physical clearances and much heavier electrical insulation.
Oh, wow.
Yeah, if an automaker tried to build an 800-volt inverter using standard silicon chips, the unit would have to be 30 to 70% larger than its 400-volt counterpart just to manage the voltage safely.
Which would instantly ruin all the weight savings we just gained from the smaller motors.
It would completely negate the benefits.
So what's the workaround?
This is why the transition to 800 volts really required a breakthrough in material science. Automakers had to abandon standard silicon entirely.
What are you using instead?
They're moving to wide bandgap semiconductors, specifically materials like silicon carbide, which you'll see written as a CS, and gallium nitride.
Okay, silicon carbide is frequently mentioned in tech spaces as this sort of super material. But let's break down how it actually solves this arcing problem.
Sure.
What does wide bandgap actually mean in practical terms?
Well, it comes down to the microscopic structure of the material. In standard silicon, the bandgap, which is the energy required for an electron to jump from a non-conductive state to a conductive state, is relatively narrow.
Okay, so it's a small jump.
Right, so when you blast 800 volts through it, electrons easily leak across that gap when they shouldn't, which generates massive amounts of heat and risks total failure.
Let me see if I've got this. So standard silicon is like a dam that's built too low. When the water pressure gets too high, the water just spills right over the top and floods everything.
That is a brilliant way to picture it.
Okay, and silicon carbide.
Silicon carbide is a wide bandgap material, meaning the dam is built much, much higher. Electrons require significantly more energy to jump that gap.
So it can hold back the pressure.
Exactly. The material can operate at incredibly high voltages and extreme temperatures without leaking current.
That's amazing.
By using silicon carbide, engineers can build advanced 800-volt inverters that are only 0 to 20% larger than old 400-volt units.
So they completely avoid the massive size penalty while capturing all that electrical efficiency.
You got it.
And this directly correlates with the data we saw in our market analysis. When you combine the lighter copper wiring, the smaller motors, and these hyper-efficient silicon carbide inverters, you get consumption numbers that look like typos.
Oh, they are unbelievably low.
Yeah, the upcoming Mercedes CLA, which was highlighted in the Electra report, boasts a combined energy consumption of just 12.2 to 14.1 kilowatt hours per 100 kilometers.
That level of efficiency is just wild. It means you are squeezing maximum range out of an incredibly small amount of electricity.
It's aerodynamically optimized, and electrically it wastes almost nothing.
But beyond the savings on energy and battery longevity, the 800-volt architecture solves the single biggest psychological hurdle for EV buyers.
Oh, I know this one. Time.
Time, the charging speed.
Right. This is where the rubber meets the road, because nobody wants to sit at a highway rest stop for an hour waiting to get home.
No one has time for that. Let's look at the charging physics here. In a standard 400-volt system, fast charging speed is generally capped around 150 to 175 kilowatts.
What happens if you try to push more than that?
If you try to push more power, the charging cables would have to be incredibly thick and heavily liquid-cooled just to prevent them from literally melting under the massive current.
Yeah, that sounds like a safety nightmare.
It is. So in practical terms, getting a 400-volt battery from 10% to 80% takes roughly 30 to 45 minutes.
Which, I mean, is manageable if you are stopping for a sit-down lunch. But it's excruciating if you just want to grab a coffee and keep driving.
Exactly. But because an 800-volt system operates at half the current, it can accept vastly more power through a standard-size liquid-cooled cable without overheating.
How much more power are we talking?
These architectures can safely pull 230 to 320 kilowatts.
Oh, wow.
Yeah, and the upcoming BMW New Class is pushing that boundary up to 400 kilowatts.
Wait, 400 kilowatts? That's insane.
That massive influx of power plummets the 10 to 80% charge time down to just 15 to 18 minutes.
So a driver can pull off the highway, plug in, and add 300 kilometers of range in the exact time it takes to use the restroom, stretch, and buy a coffee.
Yes. The charging stop goes from a major logistical interruption to just a standard rest break. It mimics the pacing of a traditional gas station stop.
But okay, we need to look at the reality of the infrastructure here.
Fair point.
The car might be able to gulp down 300 kilometers in 15 minutes, but that assumes the pump can actually deliver it. If I take this hyper-efficient 800-volt car and plug it into a standard 50-kilowatt charger at my local supermarket, I'm still going to be sitting there for hours.
Yeah, you will be.
So are the charging networks actually ready for these cars?
It is the ultimate bottleneck of the EV transition, and the electric charging report is very transparent about the logistical hurdles.
Because retrofitting the grid is difficult.
Extremely difficult. At the end of 2024, only about 15% of public chargers in regions like Germany were classified as ultra-fast.
Wow, that's surprisingly low.
Delivering 400 kilowatts to a single stall requires pulling a monumental amount of power from the local municipal grid.
So we risk having this suite of incredibly fast-charging cars totally bottlenecked by outdated infrastructure.
It is a transitionary pain point, for sure, but the networks are aggressively adapting.
Like Electra, right?
Exactly. Companies like Electra are tailoring their future build-outs specifically around this 800-volt generation. They are navigating those grid challenges to deploy vast networks of ultra-fast 300-plus kilowatt stations across Europe.
Why are they pushing so hard for it?
Because the infrastructure business model relies on high turnover, getting cars in and out quickly, so their financial incentive perfectly aligns with building stations that can support a 15-minute turnaround.
Okay, so the infrastructure is actively rising to meet the capability of the vehicles. That brings us to market access.
This is my favorite part of the shift.
Because historically, 800-volt architecture was completely exclusive to the ultra-wealthy. Porsche pioneered the concept of the Taycan, and Lucid pushed it to 900 volts with the Air.
Right, but those are six-figure luxury vehicles.
Exactly. So how does this tech apply to the everyday car buyer navigating the 2026 market?
The market shift over the last few years has just been staggering. The democratization of this technology really started when the Hyundai Kia group introduced their eGMP platform.
Which underpins the Ioniq 5 and the Kia EV6.
Exactly. They proved you could put an 800-volt system into a middle-class family SUV.
But looking at the 2025 and 2026 market analysis we have here, the disruption goes much deeper than just family SUVs.
It really does.
The 800-volt efficiency is trickling all the way down to the subcompact class. We're seeing models like the VW ID.2, the Renault 5 e-Tech, and the BYD Dolphin Surf.
The BYD Dolphin Surf is particularly notable there because it's currently running promotional pricing around 19,990 euros.
Wait, hold on. A sub-20,000 euro car packing an 800-volt architecture?
Yep.
What is the catch here? Are they stripping out battery capacity or maybe using cheaper low-grade cell chemistry to offset the cost of those premium silicon carbide inverters?
It is a completely fair suspicion. But what the market analysis shows is the sheer power of vertical integration and economies of scale.
Oh, meaning they make everything themselves.
Exactly. Companies like BYD manufacture their own battery cells and their own silicon chips entirely in-house.
Wow, so no middlemen.
None. By controlling the entire supply chain, they can drive the cost of an 800-volt architecture all the way down to the entry-level hatchback market without crippling the range.
That's wild.
The technology that was exclusive to a Porsche just a few years ago is literally now the baseline standard.
So if you are out there currently looking at a dealership lot, comparing a 400-volt car and an 800-volt car, the choice really just comes down to future-proofing.
Absolutely.
Buying a 400-volt car today is essentially buying depreciating technology.
It is the automotive equivalent of buying a 3G phone right as the telecom companies are rolling out 5G towers everywhere.
That's such a great way to put it.
An 800-volt car will interface flawlessly with the newest, fastest highway stations being built. Its thermal management means the battery will retain its capacity much longer.
And when it comes time to sell the vehicle in 5 to 7 years,
The secondary market is going to place a heavy premium on fast-charging, thermally efficient cars. A 400-volt vehicle will suffer massive depreciation by comparison.
so when you stack it all up, the physical weight reduction from needing less copper, the thermal efficiency that protects the battery chemistry, and the ability to knock out highway pit stops in 15 minutes, it becomes glaringly obvious why the 800-volt system is the most cost-effective path forward.
It really solves multiple structural problems simultaneously. It's rare that a single engineering shift provides benefits in speed, longevity, and long-term financial return all at once.
It's an absolute game changer.
It is. But, looking at the trajectory of this adoption, raises an entirely different issue, and it's something worth leaving everyone thinking about.
Oh, I always appreciate a good thought experiment.
Yeah.
Where does this take us next?
Well, we've established how brilliant this is for the consumer, but if 800-volt technology soon allows a dozen commuters to pull up to a highway rest stop and instantly draw out 400 kilowatts of power each for 15 minutes,
Yeah.
what kind of massive hidden upgrades will our national power grids need to survive that daily monumental surge in demand?
Oh, wow. Yeah, the cars are ready for the future, but the grid might be the next great bottleneck.
Exactly.
That is definitely something to mull over the next time you see a row of ultra-fast chargers lighting up on the horizon. Well, we want to thank you for joining us on this deep dive. Your time is valuable, and we appreciate you spending it exploring these massive technological shifts with us. Keep asking great questions, keep looking under the hood of the future, and we will see you on the next deep dive.